Hi, welcome to the Actuarial Data Scientist. Feel free to pause the video to read the problem, but today we are going to be talking about the chi-squared test. If you have a table of values and you know the row and column totals, so in this case, in this specific example, we'd say we know there's exactly 180 total events, and then we're going to fill out a table with frequencies that are going to sum to that amount. When you have that type of scenario, you can look at the observed counts minus the expected counts under your null hypothesis, squared divided by the expected counts, and sum that up, and that's going to follow a chi-squared distribution with n minus 1 degrees of freedom. I have the link here for the wiki derivation. Let's actually open that up really quick. And you can scroll down to the derivation, and it actually hides it because it's so clunky. And I'm not going to actually walk through this because once I saw the word Jacobian and some of this math, a little bit beyond me for the actual formal proof, but it's there if you want to look through it. The conceptual reason why this is the case is, first off, we're calling that a chi-square distribution is just the summation of samples from a normal 0, 1 and those sample values squared. So I have that written at the bottom here. And the reason that this follows that is and again, this is not, a mathematical proof or anything, but just kind of conceptually thinking about it. We have our observed counts, and that follows a binomial distribution because you can think of it as there's some true sample rate. You're taking n samples from that binomial distribution, right? So in our question, we're going to have 180 rolls of the die with a corresponding probability of 1/6, and but by the central limit theorem, we know that that's going to approach a normal distribution as n approaches infinity. So our observed frequency follows a normal distribution, and then we're just going to normalize it by subtracting and then dividing by the expected value, or I guess this would be subtracting the expected value and then divided by the square root. Again, because it's a binomial distribution. And then finally, there's the squared term, and that's how we get to this final step, which is squaring our normal 0, 1s. And finally, that gets us to our chi-squared distribution. The final thing to comment on is the degrees of freedom. So k degrees of freedom is summing k normal 0, 1s. But the problem is here that we're using, there aren't actually that many moving parameters. So actually using our problem as an example here, we know there's 180 total rolls of the die, and we know die rolls, the sides 1, 2, 3, and 4 showed up 30 times each. Now, if I told you that we rolled 30 5s, I don't even need to tell you how many 6s we rolled because you can just calculate that, which is 180 minus all of those values, which leaves you with the remainder of 30. Since that's the case, we're not actually going back to that binomial sampling that we're talking about. You're not actually getting 6 different samples. You're only sampling from 5. And that's because this 6th one is just predetermined. So again, not actually doing a formal proof, but just conceptually why the degrees of freedom is going to be n minus 1 for this table. If instead we had multiple rows and multiple columns, it's going to be n minus 1 times m minus 1, so the number of rows subtract 1 times the number of columns subtract 1. And again, for the same reason of once you've filled out that many cells in the table, just using the row and column totals, you can back into the remaining values. The final comment I have here, and again, feel free to pause and just read this if you prefer to read than to listen to me, but final comment is if n is small, so this is assuming a large n, if n is small, you would want to use a Fisher's exact test. So instead of doing this binomial approximation, which gets you to the chi-square distribution, you can instead actually calculate exact p-values. I don't believe Fisher's exact test is on MAS1, so feel free to ignore this for those specifically studying for that, but just thought I'd throw it out there. So with all that said, we can jump into the problem. So first off, we want to know our expected values. So since the null hypothesis is that this is a fair die, that is just to say each side of the die has 1 in 6 chance of showing up. Of 180 trials, that results in 30. So our expected value is 35s as well as 36s. Additionally, there are 180 total rolls and 120 of them already took place, so we know x plus y, or the number of 5s and the number of 6s, has to sum to 60. So then we can get to our actual test statistic. It's hard to say. So that's going to be the observed minus the expected squared divided by the expected, and sum all those up. So for the first 4, that's just 30 minus 30 squared divided by 30, which ends up being 0. And then finally we have x minus 30 squared divided by 30 and y minus 30 squared divided by 30. But we again know that x plus y equals 60, and so we can simplify and get everything in terms of x. So that's why we sub in 60 minus x here, and then that simplifies to 30 minus x. Next, now that we have our test statistic as simplified as we can get it, we want to know what is our test statistic threshold to be statistically significant at an alpha of 0.05. So for that, you would go to your chi-square table and look at the degrees of freedom of 5, and again, that's because there are 6 like sample values in the table, but you only need 5 before you can calculate the 6th one, so n minus 1 is just 5. And then we have an alpha level of 0.05, so we go to our table and we see that's 11.071. So we know that our test statistic needs to be larger than that. So what we can do is just set it equal, solve for x, and once we know our x, we know that then we'll come back and deal with the inequality. So first off, I just have that written here, and then this is the same as doing, so x minus 30 squared, 30 minus x squared is the same, so we can just take one of those and multiply it by 2. So we're doing 2 times 30 minus x squared divided by 30, and I did choose this one on purpose because if you choose the other one, then you have a negative value you're squaring, and then you have to deal with negative values and squares and square roots, and picking the other one's just simpler. It's all the same. So we do that, and here we're just doing a bunch of arithmetic. So we're going to divide both sides by 2 divided by 30. Then we're going to take the square root, and then add x to both sides, and then subtract off that mess. And we get a value of 17.114. So we know that if we had that many rolls of 5, that it would be statistically significant. However, if it was larger, so if it was 18, we're moving towards insignificance, right? Because the most insignificant thing you can get is a value of 30, because that would mean the die is both in the sample as well as your null hypothesis, just truly 1/6. So we know that we need to round down versus up, and that's why we get 17. Additionally, this is why we need within the problem that x is less than y, and calculate the largest value of x. Because if we didn't have x is less than y, then x could be 60, and that would definitely be statistically significant. So they could have also said x is greater than y, and then what's the smallest value of x? and then we would get, what would that be, 60, that'd be 43. But that's why they have this inequality here, because they want to specify they want the smaller of the two values. So we get an answer of 17, and that corresponds to B. As always, thank you for watching. Please consider subscribing if you find these videos helpful. Thanks.